It's a pleasure to call Professor Nimtz. Everybody knows you by now, this group. Please.
Good morning, ladies and gentlemen. First, I would like to thank the Santilli Foundation for inviting me to present a talk on the physical background and limits of superluminal signal transport. I shall give an introduction why we have such ado about nothing, yes, and then I will give an introductory undergraduate course, what is a velocity, and we will talk and I shall present an example of fast and slow velocity. That's very modern, and there is much interest also in slow as well as in fast velocity in optoelectronics, for instance. And then I will show you that tunneling offers a superluminal signal velocity. Professor Caro will show later, the last session, an example how you can transport signals at a speed more than 1,000 times the velocity of light in vacuum, and that was it. The history of superluminal, that means faster than light, or luminal, subluminal, slower than light, started 1905 when Einstein published his famous paper on the special relativity, and he was claiming that nothing will travel faster than the velocity of light, and the velocity of light is a constant, which is not for good at the moment. And everybody wanted to know which velocity is he interested in. What does he mean by a velocity of light is a limit for the velocities. And at that time, some years later, Sommerfeld and Brion make an approach to show the several types of velocity. They used the so-called Lorentz oscillator. That's a dipole, like in a water molecule, we have a dipole oscillation, and this is called the Lorentz oscillator. And they studied the interaction of an electromagnetic wave with such a dipole oscillator. And the formula for this is given in every class book. The second power of the refractive index is given by this function. This is a number of oscillators. This is the electronic charge, the mass, the permittivity, and this is the resonance frequency of this oscillator, the frequency of my electromagnetic wave, and there's a damping term. This gives the damping of the oscillator rho. Here I have given you once more, n is the refractive index, the wave number, k times n, the wave number in vacuum, k0, and the momentum is, as we know, since de Broglie, the momentum is given by h bar times k, or the mass times the velocity. Which velocity? The velocity you cannot measure directly. You have to know about the distance and the time. You measure the distance and you measure the time. You never measure the velocity. And now we see there are several velocities. we have first the phase velocity, which is given by the wavelength times the frequency f, or usually we write it by the angular frequency omega divided by the wave number k. And I have given here for theoreticians, they don't know usually these relations by heart. And the more important, particularly for applications and for signaling, is the group velocity. We can say at what velocity is a modulation, an information transported. In vacuum, everything is very nice, then everything is the same. In vacuum, we have the group velocity equal the phase velocity and even the modulation velocity. And modulation means you have modulated the carrier with your signal. My speech, for instance, or I will give you later other examples. Oh, yeah. First, I would like to remind you that the product of the frequency bandwidth of the modulation or of the wave packet times the length of the wave packet or of your signal is always larger or equal 1, never smaller. This was shown, all the IT is depending on Shannon, who has shown that the amount of information is given by this relation. There are another term, of course. Now I show you the difference between the phase velocity and the group velocity. In this example, I have stolen it from the Berkeley physics course, but I think it's very nice shown. Here you see a wave packet moving in space or in one dimension. And this is a phase. This is a phase. The phase is moving this way. And the center or the group, that's the maximum of my wave packet, is given by this cross. And we see it moves because here the maximum is here and so on. And finally, we have it here. And we see that the phase velocity is much faster than the group velocity. We are often asked, oh, we have measured the phase velocity. No, we did never measure the phase velocity. We measure the phase velocity, but this is not what we call superluminal. So you see, in this case, in this example, we have a double phase velocity, twice the velocity of the group. And this is just a playground for theoreticians. They like it very much. The so-called front velocity, but this has nothing since 1900, since Planck has introduced his constant, which is of relevance, because the front velocity is defined by the frequency component of the infinite frequency component. And you never have in a signal a frequency component of infinite frequency. Otherwise, you should have an infinite energy, because a field is only measurable if you have at least one quantum. And a quantum is given, the energy is given by h bar times the angular frequency. So, yes, please.
No interruption during the speech. I'm sorry, otherwise interrupt. No, please continue.
So, many people are arguing, and it's very elegant for a theoretician to calculate with this, because the Fourier transformation, you don't want to have frequency band limited signals. Otherwise, from the beginning on, you are non-causal. So here I have shown what Sommerfeld and Briand have calculated with the Lorentz-Lorenz oscillator, the refractive index or dispersion versus frequency, and the absorption at the resonance frequency. And the group velocity is given by this term. If we have only this term, then we are talking about the phase velocity. And this term, the frequency and the derivative of the frequency, oh, this should be a t, is, no, it's okay. That's the refractive index and the derivative of the frequency. If this term is increasing or decreasing, then we have a change of the frequency. And if this is becoming very large, then it's low, and if it becomes very small, then the group velocity is increasing. So this term is what we are talking about, and it's called in optics this normal, and this part of the refractive index, the anomalous dispersion, and this corresponds to slow and to fast light. If you are working with your frequency in this range, then you have a slow light, and if you are working in this field, then you have a fast light. Due to this expression of the derivative of the refractive index. By the way, interesting, if you measure the refractive index of glass, of the simple glass, then you will see that the phase refractive index is about 1% smaller than the refractive index of the group velocity. With your normal glass in the optics, you're still in the so-called normal range of the oscillator of glass. And it was measured some years ago directly, the difference between the group and the phase refractive index. So usually the group refractive index is smaller due to this term than the phase velocity. However, this is not the case here. This is the original graph presented by Sommerfeld and Briand, where they have shown the different types of velocity in connection with the classical oscillator, the Lorentz-Lorenz oscillator, the interaction of an electromagnetic wave like light with such a dipole. I don't think this is very good. I would prefer to have the different presentation, but this is the original picture. The velocity of light in vacuum divided by the different, that's the energy, the group, the signal, and the phase. By the way, the signal velocity was very loosely defined by them. They said if we have some oscillations of the signal detected, then we say now the signal is really coming. There are some forerunners, high frequency components, which outside the anomalous or normal dispersion, and they are moving and traveling at the speed of light. So they said after we have seen some components of the real signal, we define this as a signal velocity. However, it's interesting to see the group velocity, this one. It's always, this equal velocity equals the velocity of light. Then we have at low frequencies and the resonance frequency, we have a smaller group velocity, and there happens something. We even have a negative group velocity. And in his famous book, Briand had a footnote where he has written at that time, this is a non-physical solution of this calculation. And in the meantime, more than 20 years ago, the first paper was published where colleagues have measured the negative group velocity. So one has always to be careful with such statements. And this is the group velocity. This is the phase velocity here, oscillating. First it's smaller, and then it's even larger than the velocity of light. And the signal velocity, I think this is, yeah, as I mentioned, it's very lousy defined. It's not what we would take nowadays as a signal velocity. However, interesting is how they have calculated the energy velocity. It's very slow, particularly near the resonance frequency of the dipole. And this is although an artifact. You cannot calculate by dividing the Poynting vector, which is a vector, through the energy density. That's the way you calculate the energy velocity. You cannot use this formula in the case of reflection, because you add both. You add the total energy which is at this place, the energy coming from the reflected and from the transmitted energy. And this shows you a velocity which is much smaller because you have a high energy density compared to the Poynting vector, which is really traveling along your guide or along the air. So this is shown in the literature. I have shown it several years ago, that you cannot use this formula in the case that you have reflections. And every engineer, electric engineer, electronic engineer, knows about this problem. So this is once more the group velocity, and the group velocity, as I mentioned, may become negative, and it's really measured in the meantime. So this was classical physics, and now I show you what is a very important device since the last 20 years and is used in our long-distance fiber signaling, for instance, from Europe to United States underwater. The fiber is doped by erbium and is usually called EDFA, and the glass fiber, 13 meter long, for instance, is on a every 30 or 100 kilometers you have such an amplifier, and the amplifier is working this way. Erbium has in this fiber a 3-level system, and it's pumped by a gallium arsenide laser to this level, and then it decays to this metastable level, which is very long lifetime, 10 milliseconds. And now your signal, the 1.5 micrometer infrared signal, comes at a low level energy, and by stimulated emission, you have an amplification, as is indicated in this sketch. So it was invented about 25 years ago, and it's now used worldwide, the Erbium doped fiber amplifier, which is pumped, as I mentioned, by the simple gallium arsenide laser. And due to this metastable, you can use it to amplification. Now, I show you the data of a paper where this was used also to produce slow light. They switched off the pump laser and sent through the erbium-doped fiber amplifier the signal at the wavelengths of 1.5 micrometer. And then there was a transition, an absorption from the signal to the empty level. And the signal was damped. I will show you the results. And if you go the other way around, then you can even accelerate the signal. And this was shown in the next picture by Schweinsberger, for instance. All others, there are lots of investigations on this. Here we have slow light where the metastable state is occupied from the signal. There is a digital pulse, and you see this is the input, and the output is the time, and the output is delayed by 380 microseconds. And I don't know why they showed it this way. The fractional advancement is negative, and this is the reciprocal full width at high maximum. This is called what the engineers call FWHM, the half width here. You see, this is the definition. And they have given here the relation between them. It's insofar very important for the engineers, for the technology, because as long as the pulse is, that means as long as the half width is, the narrower on the time scale, as narrower is the frequency band. And then you have no dispersion problems. That's a problem on the fiber also. You have from distance to distance, every several hundred kilometers, you have to reform due to the dispersion change, reshaping of the signal. You have reshape it once more to the properly shape. So here we see this is measured, or no, this was measured with a power of 0.8 milliwatts. And here they applied, on the pump, only on the pump power. And then the signal was amplified by stimulated emission from the metastable state. And here we see that the delay has a positive advance. That means the output is faster than the input. And what they have in this experiment here, we see that's the velocity of light in vacuum. They came down here, down to 25,000, and here even to a negative velocity of 3,000 meters per second by this process. So So you can, with this system, with this erbium, there are several other systems, but they are much more complicated. This is done by room temperature. All the other slow, particularly the slow experiments, were done at very, very low temperature and organized to such a configuration of states and of levels. Now I show you what means that once more. Here we see a sketch of the shift, the delay. If it's positive, then it's slower, the group velocity. Then C, if the delay is 0, then we have, according to the relations, then we have C, and if we decrease, becomes negative, then we have superluminal, a range of superluminal, and there's a pole, and then we have eventually a backward. This is shown here, illustrated. This is the medium, and the black one, this one is superluminal, comes earlier on the time. That's former before this time. So this is the original pulse, and we have even backward. This is also used in electrotechnology, the backward, and that means it's out before this was in. That's funny. It comes out before it comes in. It's the maximum. I will come back to this later. It's not the real shape. I have shown you this packet, and I want to clear. We have seen this packet, and the packet is always shown on the right side for the field, for the electric field or for the magnetic field. However, the other presentation is the power. And this is such, if you square it, the energy is proportional to the second power of the field strength of magnetic or of electric field. And then you have such a pulse instead of this wave packet. And now I show you what they have done on the glass fiber with the erbium doped amplifier. And here we see a typical what we are using every day. If you use your telephone and call Mr. Santilli in New York or in Florida, then it goes on the glass fibers through the ocean this way. And here are the digits. And this is what you see here, that's power. And therefore, I have shown you before the wave packet. This is a wave packet always. And this one. So here are the digits 1, 1, 0, 0, 1, and so on. Now I have talked about classical. There was only the three-level system is not purely classical because simulated emission is not a classical process, I would say. And now I come to a non-classical process, a tunneling process. We talk about tunneling if the energy of the particles, independent whether it's a photon, a phonon, or an electron, or quite recently several experiments were carried out with electrons and showing that they tunneling in 0 times through such a barrier. That means the energy of your incident particles or ensemble of particles. Here we have an ensemble of 4. 3 are reflected and 1 is transmitted. And the wave number is in this case imaginary. This is the potential of my barrier, the height, and this is the energy of the photon, electron, hadron, whatever we send. And here we see what was done by technicians of Corning more than 10 years ago. They tunneled on the fiber such a digital signal, and they obtained an advancement at the velocity of 5 times c. This is their signal. And the slow one, here we see the dispersion of the barrier. This is a forbidden range where the potential is higher than the energy of the photon. And this is a spectrum of such such a digital pulse. Oh. No. Come. You see, it's very narrow. Gigahertz versus 2 times to the 14th of the 1.5 micrometer carrier frequency of the infrared pulse. However, the bandwidth is very slower than 10⁻⁴. Nowadays, using the smartphone, you are using UMTS. This has a much broader bandwidth in order to transmit more signals better. You would not, the classical system.
Herr Nimtz, you have 15 minutes. If I may have a suggestion, the next 10 minutes perhaps go to your main aspect. And so we have 5 minutes left for discussion. We have to have discussions on this.
So, this is an excellent example how you can transport superluminal signals on the glass fiber. And we had this joke, Eichmann, many years ago. This is AM modulated amplitude, and we have done this with music on a FM modulation. So this works. Here's another experiment who shows you that this is very interesting because we did not measure the transmission, we measured the reflection. And the reflection time is the same as the transmission time in the case of tunneling. And here you see, if you reduce the barriers, this is a barrier. Such barriers are used in all the laser technologies because the lattice is the dielectric lattice is much better, has a better quality than a metal reflector. And what we have shown is that the back mirror, if we have a metal plate here and reduce the lattice, and of course the intensity is smaller of the reflection, but always the time is the same. That means at the front, the signal knows how long is the barrier and how high. And its time for the reflection or for the transmission, that's called the Hartmann effect, is independent of such a barrier length. So once more, and now I show you what I mean with pulse reshaping. All these classical experiments about which I spoke at the beginning are having this type of reshaping. That means here, entering the medium, and this the maximum comes out before the maximum of the signal, of the original pulse, went into the material, into the medium. Pulse length may be the same. However, the detector has to wait. He started to measure and ends up, and then he can say, my digit is 1 or 2 or 3. And in the case of the tunneling barrier, you don't have this problem. If the bandwidth is not too large, again, but the bandwidth, as I mentioned several times, is always a problem, then you don't have this. You have also a complete shift from the beginning up to the end of the measuring process. Now I come to the summing up. And I concentrate on tunneling now because we will show you later this. In tunneling, the refractive index is purely imaginary, whereas in the classical processes, the imaginary part describes the losses, the damping. And the phase time, this, which was introduced by Wigner, is used to calculate or to measure nowadays the time in the case of an imaginary wave number, as we have in the case of tunneling. That gives you a 0 time inside the barrier. Whereas in all the other mechanisms, you have an interaction as long as you in your medium. And we found another interesting behavior, that the scattering time or the transmission time is a universal number. For instance, 1 over the frequency of the barrier, of the packet, or h divided by the energy. And as I mentioned at the beginning, we have found this for photons. For phonons, that's very interesting. For phonons, the elastic particles have the same behavior. And recently, several papers were published in Nature and in Science that they have measured electron tunneling in 0 time. That means, again, you have only a time which was predicted by Francis Lowe, for instance, by this relation. Now I'm finished. He stopped me already. Thank you very much for your attention.
You still have 5 minutes left, please. I just reminded you we had 15 minutes available.
Oh, sorry.
I did not stop you. No. Please, if you have more to say, please. You have more 5 minutes.
Yeah, no.
It's a crucial point, if you could elaborate.
No, I think we discuss it now. I stop here at this point, and if you have questions, please.
The question, I'm sorry, I could not allow, because if we start discussing during lecture, the lecture will never be completed. But also your discussion may not be of interest to the others, so you kind of disrupt so no interruption during the lecture. But after, yes.
Okay, thank you very much. I have a couple of questions, but first start with front velocity. Is it real or not? The first question, that you have shown that energy is bigger than or equal to h bar omega. It seems not, but I will ask this question first to you. Is it real? And the second one, when a signal passing through medium, just for superluminous signal, it reverses the signal, isn't it, then? I mean that you have shown us that the last part of the signal comes out first. It does mean that signal is reversed. I mean that, for example, when you have the Mozart symphony pass to the other, it starts from the end to the something like that. That's it. Thank you.
Could you repeat it?
Okay, one by one then. Okay, first, front velocity. Is it real, physical?
Sorry?
Front velocity. You have shown that classically it is defined that front velocity Vf is equal to limit omega goes to infinity, omega over k.
He wants to know if the front velocity is real
Or not.
or just fictitious.
Yeah.
That's a real velocity. You have.
It is bigger than h
It's
bar omega.
measured. It's measured. You always have to realize that you can measure only a signal if you have the energy. You measure energy, not the signal. If you don't have an h bar times omega, you have no field, no signal.
I mean that it's bigger than h bar omega. That's why I have asked if it is real. Okay. Then superluminal velocity, you have shown that medium, when a signal passes through the medium, first the last part goes out or passes to the other side from the medium. Does that mean that signal is reversed? I mean that's something like speaking from the left-hand side, or speak K, E, A, E, something like that. Is it like that?
You mean the backward signals?
Yeah.
Okay, that does not work in the case of tunneling. In the case of tunneling, you have a superluminal velocity up to 10,000, 100,000, but you never come to a negative. This is done with an extremely classical anomalous dispersion relation. Or here in the case of the stimulated, of the absorption or stimulated emission. In this case, you can do this in this case of stimulated emission. But then you have a reshape, what I have shown you. It's reshaped.
Please identify yourself because we are
Okay.
But you have seen the formula.
Yakup Unda from Turkey, Istanbul Technical University.
You have seen the formula. If this term is larger than the classic, then you have a negative, and I have shown you on the how large the delay must be in order to get the backward. Here you see the diagram of that's the delay or the advancement, delta t. And if this comes out after on the time scale, before, that means before here, that's later, then it's positive, then it's superluminal. However, if the delay is so long, negative, then it's even out before it's in. And that's called backward. It's the maximum of your pulse. And this is shown here by this relation that when this happens. If this is 0, then you have this pole, and if it's still increasing, then you have the negative as a backward movement of your signal. Of the maximum, that's not a signal, that's a group.
Any other question, please? I think yes, I think it's first.
So when you say negative velocity, you mean sort of a reflected pulse? It's moving backward instead of forward.
Yeah.
So
there are backward microwave amplifiers available, really.
So In other words, to send a superluminal signal, you would send it in the wrong direction, right? In the opposite direction, and you get the backward pulse going superluminally,
Yeah,
reflected.
but it's only the maximum. I have shown you how it's reshaped such a signal. But for some technical devices, it's okay. It's
And
useful.
could you please repeat what is the longest distance you've done the experiment to send superluminally?
Here we have 50 meters. 50 meters, that's the
50 meters
waveguide.
today.
10 gigahertz,
Well,
3 centimeter wavelengths, 50 meters. You will see in the last lecture. No, in the last one, after the coffee break. Yes.
Professor Nimtz, I have two questions, one particular question and one general question. My particular question is that you said that in case of photonic barrier, not only transmitted wave, but also reflected wave is superluminal. But reflection, it seems to me, can be described in quite classical way. Therefore, therefore you have some boundary, you have a falling wave and a reflective wave, and therefore this is a quite classical process.
Mm-hmm.
But in this case, you also claim that reflective wave is superluminal.
With?
Superluminal.
Yeah.
Yeah. Why? What is
Because inside the barrier you don't lose time. There is 0 time.
But
It's non-local.
now we speak about reflective wave. It does not pass across barrier. It reflects.
I have shown you or tried to show you the reflection time is still has the same time delay as the transmitted. It's 1 over the frequency of the carrier. And inside the barrier there is no time left.
So
Independent
you have
on the
some
length, yeah.
barrier. I can understand that between this point and this point we have no delay, time delay.
No, it's 0 time.
The 0 time.
Yes,
Yeah.
I agree. But it's a case of transmission. But in case of reflection, reflection occurs from the same point.
Yeah,
Like
the same time. That's exactly what I wanted to explain.
no, maybe,
Whether it's reflected or not reflected, you measure a
maybe
delay.
we will discuss it a bit later. Now, my general question. Many theoreticians claim that the allowance of superluminal signals is strongly forbidden by classical causality.
Yeah.
In particular,
Oh, that's fine. That's good, this question. I like it very much
That I would
because
like to discuss myself.
what do you think about Penrose's proof?
that's
That it's because, for example, I disproved this proof by Penrose some time ago. But what is your own opinion? And
about 10 years ago I have given several times a proof that you don't disturb causality. You only confront the Einstein causality. Because that's now the problem. In all the books on special relativity, the signal is given as a point in time. And that's not a physical signal. And if you use a physical signal, as I've shown you, the digits from the glass fiber, for instance, then you have a product of delta t times delta the frequency. And if you start, I can give you later a paper where we have shown how you start in the past. However, your signal, if I say a word 4, then you have to wait up. I have completed my 4. 1, 2, that's the signal. And the signal is always ending up in the future.
okay, maybe
No, that's not. That's really, you cannot disturb. You cannot confront. Yeah, this is ridiculous.
Well,
this example with Lotto
I would like to interject myself in this conversation because my point is connected with Professor Kolmensky. Professor Nimtz, we have a friendly disagreement that is 20 years old. I remember in 1992 I was informed about, I was in Cambridge, Massachusetts, I was informed about your experiments, and I consulted immediately the local physicist, and I immediately had this type of objection. Then I sent you, I contacted you, maybe you forgot, but in 1993, immediately after publication of the Iso-Minkowski geometry, I contacted you. And our disagreement is the following, that, well, there are several disagreements. Yesterday I invited Professor René Verroel to criticize my work on iso-redshift because we have to listen to objection if we want to really have our discovery being accepted by the scientific community. Is it the same in your case? You have to listen carefully to the objection because, there is a realistic chance that they are sound. In my opinion, I agree with Professor Kolmensky and with what is the general consensus, namely that the way you interpret your experiment, which is via conventional classical mechanics in empty space, via special relativity, violates causality. This is my opinion. Please respect that I respect yours. The reason why I contacted you in 1993 is the second, perhaps the biggest disagreement that we have. I respect your view, respect mine. You do not have what you claim, namely a system in empty space. No, here it is. Look at everybody. It is a physical medium. So since it is a physical medium, you implicitly assume that Einstein's special relativity is valid between all those barriers. That's our disagreement. Incidentally, my proposal was to help you, but I failed completely so far. Because the moment you admit that your superluminum setup is in an interior dynamical problem, it occurs within a physical medium, Einstein's special relativity no longer occurs. Let me put it in a different way, and I conclude. The moment you compute all the calculations that you have done, you computed them, which is everything you have stated is in empty space. That's Minkowski. The moment you reformulate, particularly the zero time, the barrier, you have a tunnel effect within the physical medium. All the objection that you have, they collapse to zero. So I try to make this recommendation to protect your results. But you never accepted the reality that you are working within a physical medium. So you have to recalculate the barrier, the tunnel effect within a physical medium, not in empty space. It was made in your support, not to criticize, so that the causality issue is removed. The moment you admit the physical medium, the causality issue, speed is arbitrary. You have not seen yesterday all the evidence for the arbitrary speed within a physical medium. That's the end of my speech.
We have tunneled also in the vacuum. Yes. You know the double prism.
Yes, but not superluminal. Yes, of course we have tunnel, but not superluminal. The electrons that have been propagated, they are not superluminal, they are subluminal. That's the whole issue. Because
what is a superluminal what?
I'm sorry?
I said we have tunneled through the vacuum of the double prism.
But that is not that's
not the medium.
It is a prism.
Vacuum, no, that's vacuum.
The prism, everything you depart from purely empty space, you have an interior problem. Oh my God. No, you cannot say this in vacuum. Everything you have,
of course.
Everything you have an electromagnetic waves.
We crossed the gap is vacuum.
It's not the question of the gap. It's the question of the moment you impact. The moment you impact the prism. You mentioned the prism. You are not in vacuum.
Otherwise, you don't have a barrier. You must have a barrier.
But that's the whole point.
For the tunneling process.
But that's the whole point. The tunneling does not occur. They cannot be formulated in empty space. There are inconsistencies in the formulation.
It's on the border, on the front.
Yes, because the moment it hits the surface of the prism, that's no longer an empty space.
So anyhow, this is my view, and incidentally, it's to protect you, because the moment you admit that the prisma, the electromagnetic wave hits the prisma, it's no longer in empty space. But then the causality of the tunneling is totally eliminated. Totally eliminated. For your protection, not to criticize you, to protect your results. This is all my viewpoint.
Contribute to your discussion.
I'm sorry?
Mainly to contribute into your discussion, because I partially agree with both these opinions, but at the same time, I'd like to remind that in recent experiments of my research group, we just observed a superluminal propagation of bound electromagnetic field in vacuum.
That is also a possibility, yes.
Yes, therefore, in my opinion, you are both right.
Case, you speak of classical electromagnetism. Is a consequence of Maxwell equation, which indeed is a consequence of special relativity.
Yes.
We don't have a contradiction.
Wait, this is
Yes. In that case, when you perform this kind of tunnel, you are using Maxwell equations. We are a direct consequence of special relativity. Then there is not contradiction in my view. There is a superluminal solution, but it does not contradict Einstein's special relativity.
I can say that in my own opinion, special relativity can be easily generalized to adoption of general relativity principle in empty space, where we have that is, any phenomenon can be described from any admissible frame of references. Okay.
Yeah, there is an ambiguity here that we have to clarify regarding your statement, Professor Kolminsky, that the electromagnetic wave propagated in vacuum. Maybe yes, maybe not. What is important is the capability of propagating signal, a usable signal. That was, I do not know whether it's been done by those waves. In other words, you can have a front many speed, but the question is whether in vacuum, via an electromagnetic wave in vacuum, you have been able to propagate an information, usable information, the group velocity. That I have done, because if that's the case, then Einstein's special relativity is violated in vacuum. So I have extreme reservation on that.
We talked always about useful information.
Yes.
Yes. And here we have a vacuum.
Yes. Well, but in between the barrier.
Yeah, there's a virtual particle.
No, but in the barrier you have zero time. It's not
It's a barrier.
In between.
But it's funny.
In between is
that vacuum represents a barrier, and is used nowadays in optoelectronics. They couple, for instance, two fibers by vacuum to tunnel some part of the signal.
Yes, one.
So it's fortunately that you have this slide, and my interest is to know about the distance d between the prism. It's a distance of a barrier.
This is it. Yeah, exactly. That's
It is a barrier?
air or vacuum.
Yes, and what is the physically, you made these measurements, what is the physically in centimeters? How much?
The physics is that we have sent a signal.
No, it's a d. How
and
much?
We measured the reflection and we measured the transmission.
Yeah, I know.
And,
I know.
And
how much d
time,
is? How much?
Sorry?
How much d
Yeah.
is in centimeters? How much?
What?
The distance d.
Sorry. This was carried out at 10 gigahertz, that's 3 centimeter, and we have up to half a meter.
D is up to half
Yeah.
meter.
But however, the problem is tunneling. If you have too long and too high barrier, then it's more and more reflected. That means signals, or original signals, attenuated. We usually work with 30 decibel damping, but that's from fortissimo to pianissimo. That does not mean that the signal got lost. The people don't understand that forte or piano is the same information, only loud or...
So D is up to half meter.
Yeah, that depends on your equipment.
Any question, please?
And
We have to-
may I show you another picture? Because with, we have also shown, this is, by the way, inside the virtual photon here. In such vacuum, you have just a virtual, you cannot measure it, by the way. Nobody can measure a virtual particle, but it has to be there because we measure it on the other side.
So it is not very small, it is quite big distance.
And here we have proven why what the problem is with the special relativity, why it confronts, and why we cannot design a time machine. Because a signal, and this is always in all the books I know, this is our signal, you see here. And it is sent when the counter of the lottery is closed to another system at superluminal speed and sent back and arrives before the counter closed. So you know this example in the textbooks. And however, the signal, you have 260,000 that need some time. And my calculation has shown that you always end up with your signal in the future, even if you begin with your number 260,000 in the past. Always. You are faster, but you cannot go completely back into the future with your signal, with your information. Because this is my digital pulse, for instance.
Sorry, may I ask you?
You understand? Understood? That's really a problem by the dispersions and.
Did you consider the polarization effects? For example, in medium, where you have a circular polarization, you have different velocities for the right hand and left hand vector of polarization. So, did you consider linear polarized waves, circular polarized wave, and where exist different velocities in this package for left-right, left-hand polarization and right-hand polarization, for example, in circular polarization case?
Did you understand? No, sorry, we didn't understand your question.
So,
Both of us, fortunately.
if a circular polarized electromagnetic wave penetrate the transparent medium,
You are talking about polarized?
polarized.
Yeah,
Yeah.
they are polarized waves, for instance.
Yeah, but
But
why-
we have done it with different polarization, and we will show you even circularly polarized waves. Yes?
And in the case of polarized waves, you have different, in classical case, different velocity in the medium.
It depends on the medium, but not in the case of a barrier.
No,
in quantum
in a
mechanics.
medium. So,
Yeah.
but you have such effect in the...
No, we never did this in classical media. We only carried out experiments with tunneling for superluminal signal transport.
And the second question, Sommerfeld made a research which, for example, his interferation picture is phenomenological. We cannot describe it solving the Maxwell equation. And all your experiments, they can be described by classical Maxwell equation, quantum electrodynamic equation, or... So, all your efforts you are considering, can I show it solving the classical electrodynamic equation or quantum electrodynamic equation, or there is no such results?
Now, the superluminal behavior comes through the zero time inside the barrier. The wave number is imaginary, and according to the phase time, you have no time. And that's what we measure, really measure, that's no time. As I have shown you before, it's very obvious in the double prism, where you measure the reflected at the same time as the transmitted. Even the transmitted has a longer distance traveled.
I'm looking in theoretical research.
Yeah, then you shouldn't use, you should read Shannon, for instance, about a signal.
Ladies and gentlemen, we'll have a second round of discussion after Dr. Carroll.
Yes,
Dr.
we
Carroll,
can
please.
discuss later.